Hi everyone, I'm Yiping Huang. It's my great pleasure to introduce our team to the best and brightest prospective students. I hope you would like to join the adventure with us. Here's a brief introduction about myself. I graduated in 2008 from this building. I worked with Professor Dao Wang when I was a undergrad student on the co-atom and quasi-one-dimensional physics. And after that, I moved to the US. I joined the PhD program of the University of Colorado Boulder, and there I explored the physics of topological order and spin-orbit coupled materials. And after I graduated in 2017, I moved to Max Planck Institute for my first postdoc. And there I focus on the dynamical quantum phase transitions in constraint systems. And after my first postdoc, I got a Marie Curie fellowship and continue my second postdoc in the ETH area, basically the PSI Institute. And there I have the opportunity to explore the effect of impurities and how the gapless modes mediate interactions between these impurities and drive the system into novel orders. So I'll characterize my uh, theoretical physics taste as I would like to, and I love to combine two novel ideas and try to fuse them and develop a third different scenario. And using that scenario, I can develop a different research topics and the different research area. So to be more specific, I listed what are the interdisciplinary nature of these subjects. But the bottom line is basically the systems that I have been studied, including quantum magnets and also the synthetic quantum matter, which are basically co-atoms. And I will try to fuse these ideas or these settings to explore novel theories. My current research interests are also relatively broad. However, life is short, so I need to identify what's the important structure. So, to me, the common theme is on the emergent structure of many-body Hilbert space. The subject have developed multiple interesting directions in my group now. I list them here, but due to the limit of time, I will only introduce our recent breakthrough on the quantum ergodicity breaking, and that will be the subject called interference caged quantum many-body scars. I will here give you a brief understanding why emergent structure in the many-body Hilbert space is so exciting or a right area uh, to discover new physics. The point is that quantum system has non-locality built in, and if you ask yourself where the non-locality uh, manifests itself, it's basically in the structure of the Hilbert space. And in addition to that, if you learn quantum mechanics at the very beginning, you know there's a particle wave duality concept. And interference is one of the core subject of quantum mechanics. And if you think about like how entanglement and how other novel properties that can be used in the quantum technology, they are all related to the non-locality and interference. So that's why I think exploring the many-body structure or like the structure of the Hilbert space due to the many-body effect is a very important future subject, at least within the 5 to 10 years span. Okay, so here's a very brief introduction about the concept of interference cage quantum many-body scars. This work is collaborating with my PhD students, Daolin Tan. So we basically try to fuse or try to ask a question that is sitting at the corner that intersect with three different subjects. One is the quantum ergodicity breaking, and the other is the flat band physics, and the third one is more mathematical. It's related to the graph automorphism idea. So let me briefly introduce what we mean by ergodicity breaking. So in a quantum system, you need to define your Hilbert space and you need to define your dynamics, basically your Hamiltonian. So the Hilbert space usually is represented by bases, and dynamics basically tell you like how these bases are, coupled with each other. So this idea can be captured in a very general sense by a graph that's called a Fock space graph, and I already plot them here. You can see this complicated or this complex network, basically the um, the Fock space graph. So for a Gothic system, in the statistical mechanics sense, it means that your wave function can evolve to every corner of your configuration space. But in the quantum system, the so-called configuration space are basically formed by the Hilbert space or the basis. So for a thermal state, you anticipate that it should be structureless. Everything is relatively complicated, just like a figure 8 here. And for the non-thermal phase, you basically want it to have certain kind of pattern or some regularity in this complicated system. So what are they? So we try to answer that question in a positive way. So basically we said that, look, this is a quantum system. The most general effect in a quantum system is basically interference. So I ask, or like we ask, what could interference leads to a non-ergodic or a regular pattern of your eigenstate structure? So here we demonstrate two of them. One is the so-called simple interference cage quantum n-body scars. So what happened is that this interference will confine themselves through a destructive interference pattern such that they have some relatively regular structure. So we call them simple because they are relatively fragile. Once you have some perturbation, then this eigenstate will degrade it into this thermal state. So what is novel or like new for our new scheme is this topological interference cage quantum n-body scars. So basically what is happening is that the probability weight is confined in a small corner of your complicated Hilbert space like this. So you can see that this red point means it's of like positive weight, and the blue point represent they have negative weights with the same amplitude. And while they hop from one side to the other, they form perfect destructive interference on these white vertices. So that's basically the idea of interference cage quantum n-body scars. So why it is related to flat band physics? If you know, Kagome lattice or particle lattice, and what's the origin of flat band physics? This physics is exactly reproduced there, and in fact, in the simple cases of the flat band physics, the lattice is the real space lattice, and here we just develop this idea on the Fock space graph. And how it is related to graph automorphism, because in order to have perfect cancellation, you need to have the right amplitude to cancel it. That means that you need to have a symmetry principle support this structure. And on a general graph, the symmetry principle is studied by mathematicians, and that's called graph automorphism. So this is the type of research that I'm excited about. Basically, you try to combine different research area and maybe add very different cross-disciplinary ingredients and try to address the thorny question of ergodicity breaking in the quantum systems. Okay, so the impact of ICQ-MBS has emerged after we posted on arXiv this year, April. And after our preprint is online, we attract, first three citations from the world leading groups. It is even before official publication within a month. So the first one is by Professor Roderick Mosener from the Institute of the Max Planck Institute. He's the director of the Max Planck Institute. And the second one is from Professor Maxim Sabin from the Institute of Science and Technology, Austria. He is the basically inventor of the idea of quantum n-body scars. And the third citation is from Professor Frank Pullman, who is a pioneer in the study of symmetry protected topological order and various numerical techniques related to tensor networks. He's from TU Munich. And the independence discovery of this idea through three independent groups actually is a very strong support that our idea is correct, and people are interested on an international scale for this kind of discovery. So right now it is at the very beginning of the subject, and there are more questions than answer now. So here I just show some of the invited talk on this subject, and to convey that this idea is really spread to an international level. So I got invited talk from Japan and also China this year. And in the next year, I'll get an invited talk from the European system, basically the DPG meeting. That is basically like the Europe version of APS meeting. And also, I got invited to the international workshop of the Max Planck Institute. All right. So here are several goals in our group in the coming years. The first one is basically push the already world-leading discovery on the ICQ MBS and try to develop a more complete framework for this idea. And there are some emergent world-leading topics, including the duality dynamics and discrete scale invariant tensor networks and other subjects. But due to the limit of time, I'm not able to talk about them right now. So the goal of our group is actually not just building the hub. The goal of our group is actually we want to cultivate future researchers. So the research background for our group include quantum mechanics and statistical physics and many-body physics, but you need to learn them by doing instead of taking courses. And also, the mindset to join our group is that you need to have interest about this subject and you are self-driven to learn these things. And you need to be patient about yourself and trust yourself that you are getting better and better during the time. So why it is so? Because we are targeting unknown problems. You need to be brave and persistent to explore this new physics where nobody in the world knows how to deal with it. Okay, so here's um, the metaphor that I hope you can understand a little bit about how it is like to do theoretical physics. So it's just like hiking. And me, as a group leader, my goal is actually to find the right mountain or a good mountain to climb because life is short, you cannot climb all the mountains. So for me, I tell you which mountain to climb, and I'll try to assemble a team that can climb with you. For yourself, the duty is basically you need to train your legs, basically do some physical training to guarantee that you have a strong leg, to learn the old theories, to do literature search, build your own way of understanding things and presentation and paper writing, etc. And while you are interacting with with our team, you learn to tell what is the right direction to go because this is like the independence you need while you are becoming a researcher. So you need to discuss with theoretical physicists, you need to discuss with experimentalists, mathematicians, sample grower, all people that is within or outside your comfort zone. So that's like the logic and the mindset. And here are several people in our group, but I probably will not have time to tell you who they are, but feel free to contact them if you want to know how it is like to work with me. And if you have any questions, you can contact me through this email and you can check our website. And here are several keywords that you are able to Google around. So thank you and looking forward to work with you in the future.